We're moving now to Chapter 8 to learn different techniques of integration. The first one we're going to talk about is integration by parts. So in the same way that use substitution was used when we're trying to reverse the chain rule, we use integration by parts to reverse the product rule for derivatives. And so just to make sure we all remember our product rule, I'll go through an example. In order to find the derivative of f of x equals 5x cubed e to the 2x, you want to, first of all, envision your function as being made up of a product of two individual functions. And usually we don't worry about the constant, just let it hang out with whatever's there, but split between the two major functions. Then when you take the derivative, you keep the first function as is. So my 5x cubed stays 5x cubed times, then I take the derivative of the second function. So the derivative of e to the 2x requires chain rule. We're going to keep the base of e and leave the inside stuff, which is the exponent, the same, and multiply by the derivative of the inside stuff. Derivative of 2x is 2. Plus, then you just reverse it. So we left the first function the same, took derivative of the second one. Now we leave the second function the same and multiply it by the derivative of the first one. Derivative of 5x cubed is 15x squared. Then all we're left to do is a little bit of cleanup, multiply our constants together, and this would be our final answer. So here's the theorem for integration by parts. If you're working with two differentiable functions, u and v, then this rule is going to hold. It says you can change the integral of u times dv into the product of u and v minus the integral of v du. So what this does in essence is it switches up an integral that you're struggling with into a different integral. But in order to be equivalent, you have to also do all of these steps in this expression. And the second statement here is just the exact same rule, but how it would be written for definite integrals. So it only makes sense to try and do this if you end up in a better place after you apply this rule. So things to keep in mind: you have to be able to integrate whatever you let be your dv in order to get back to the original function v, and the integral of v du must be simpler or more familiar than the integral of u dv. So let's take a look at some examples. In example 2, part A, we're asked to evaluate this integral. Now, I kind of see a natural division between two functions here. And at this point, I haven't given you any sort of pointers as to how to choose what your u is going to be. And again, we're not performing u substitution. It's just a coincidence that we use the same letter for this process as well. So I'm going to let u be the first function, which is x. And then I'm going to take the derivative of u, which is, of course, dx. Now, unlike u substitution, I will then set everything else equal to dv. So I take the entire rest of the integral, including the dx, and call that dv. And then I'm going to integrate dv, which means I'm integrating, in this case, e to the x dx. And when you integrate this differential, it just becomes v. The integral of e to the x is e to the x. And we will put on a constant, but we don't need to worry about that yet. So this is the setup process for integration by parts. You'll choose a u function, and then you will take its derivative, and then you'll assign the rest to be your dv function, and that you will integrate. Next up, you write your formula for integration by parts. On the left side, my u is x, my dv is e to the x times dx. So on the left, you're just confirming that you are evaluating the integral you're asked to evaluate. Then on the right, you do u times v, so x times e to the x, following my information up above, minus the integral of v was e to the x, times du, and du was dx. This is the second point where you kind of stop and pay attention to what you're doing with integration by parts. First of all, you make sure your setup's going okay. If it is, you proceed. This is the next place where you want to kind of get a readout of how it's going. So I have now switched the integral I was given into a simple product minus a different integral. It's important that I'm able to actually evaluate this new integral. If I'm not able to evaluate it, then I need to go back to the drawing board and try something else. So in this case, I'm good to proceed. So I have x times e to the x minus integral of e to the x dx is just e to the x plus c. At this point, I would put on my constant, and I have evaluated this integral. Now, part B is actually the same integral, but we have limits of integration. So this is a definite integral. Here's my formula, and again, I prefer the double-sided bracket for the antiderivative stuff, so I would put a bracket in there. You do the exact same setup and substitute each of the parts. Okay. Substitute using the fundamental theorem of calculus, which gets you to this point. 1e to the first is just e, minus 0 times anything is going to be 0, minus an e to the first, minus, you've got this e to the 0 here, which is 1. So you're really subtracting a negative 1, which is the same as adding 1. The e's drop out, and your final answer is 1. In our next example, we're given an integral that involves a product, and we're adding the additional step of checking the answer by differentiation. So again, I have not given you any guidelines whatsoever in terms of choosing u. So I'm just going to find the natural breaking point here. I'm going to let u be x squared. I'm going to let my dv be everything else. On the left with u, I'm going to take the derivative. On the right, I'm going to integrate. Now, when you get to this point in the integration, you need the integral of the natural log of x. That is not 1 over x. It's the derivative of natural log that is 1 over x. Natural log of x, we don't have a formula for at this point. So I'm kind of stuck in terms of the setup process. And this will very often happen when you're doing integration by parts. And you have to understand that most often you're going to have to try different things to get all the way through to the end. It requires perseverance. So what I'm going to do is I'm going to just leave that sitting there, and I'm going to opt to switch up my u and my dv just to see if that makes things any better. And notice when I'm writing my dv, I automatically keep the dx with that one. You don't put the dx in the u, you want the dx in the dv. Taking the derivative of u, derivative of natural log of x is 1 over x dx. And if I integrate this side, dv becomes v. And the integral of x squared, of course, becomes x cubed over 3. So I made it through the setup, so this seems more promising. So for the time being, I'm going to ignore my first thought, and I'm now going to go to the formula and see if my integral that gets created by the formula is going to allow me to continue. So on the left-hand side, when I substitute u and dv, I get my original integral back, but in a different order. That's fine, they're equivalent. Then I do u, which is natural log of x, times v, which was x cubed over 3, minus the integral of v, x cubed over 3, times du, and du is this 1 over x dx. So what's critical at this point is that I check this new integral and see if this is something that I'm going to be able to evaluate. First, of course, it helps to simplify it. When you have this x in the denominator and x cubed in the numerator, you can cancel out one of those x's, and you're going to be left with a numerator of x squared, and in the denominator still a 3. And this is an integral that I can work with, so therefore I am definitely on the right track. I'm going to keep going by performing that integration. When I add 1 to the exponent, x squared becomes x cubed. And then I'm supposed to divide by 3. But keep in mind, there's already a 3 down there. So I would multiply those together, and it will become a denominator of 9. And I would now put in my plus c. So that is my answer. I no longer have any integrals in my expression, so I'm done. And as I said earlier, we're going to check this one. And to do the check, because integration is the opposite of taking a derivative, we're going to take the derivative of what we got our answer to be and make sure that we are getting back the original integrand. In order to take the derivative of the first term, this is a product, so therefore we need to use product rule. So the product rule for derivatives says you keep the first function the same times the derivative of the second function plus the second function stays the same while you take the derivative of the first function. Now we would bring the 3 in front, which is going to cancel off the denominator and leave me just with x squared. Next, I take my derivative of x cubed over 9. Again, I would bring a 3 in front. So I'm going to have minus 3x squared over 9. And I can reduce between the 3 and the 9, leaving just a denominator of 3. And when you take the derivative of a constant, it disappears. So we simplify the first term, put the algebraic part of the second term in the front, keep the third term the same, and you'll notice first and third terms cancel out, leaving me with x squared natural log of x. And if you go back to our original integral, that was the function we were integrating. All right, we're going to go through 2 more examples. Now, in example 4, it almost looks like we don't have a product. But you have to remember you've got this differential there. So the place where I would want to imagine splitting my functions is right there. I'm going to let my u be natural log of x, let my dv be dx. Derivative of u is just 1 over x dx. And when I integrate dv, it becomes v. When I integrate dx, it becomes x. So my setup went just fine, and now I'll go to the formula. Substituting on the left, I get natural log of x dx. Substituting on the right, u times v is natural log of x times x minus the integral of x times du, which is 1 over x dx. I'm going to bring the algebraic part in front of the log minus. These x's in the integral will cancel, so I'm really just looking at the integral of 1 dx, which is just the same as the integral of dx. And that's a nice simple integral that just becomes x. So this one went quickly, and we got to our answer here. And incidentally, that's the formula for the integral for natural log of x, which we were talking about in an earlier problem. All right, one last example in the basics section here. Now I'm going to go ahead and see the split of my functions here. I'm going to choose u to be my first function, dv to be all the rest. Take my derivative of u, and I'll get 2 dx. And when I integrate dv, I have to take the integral of e to the x squared dx. And be careful here, because it's not as simple as just saying, oh, it's just going to stay e to the x squared. We have a function of x up here instead of just an x, so that becomes a more complicated integral. So it looks like this is one of those times where I'm kind of stalled in my setup, in which case I'm going to consider switching up my U and my dv. And again, please get used to needing to take more than one attempt to get things started. So U will be e to the x squared, and dv will be the 2x dx. Now, taking the derivative of u is possible with the chain rule. Take derivative of e to the x, it's e to the x. Keep the exponent the same, times the derivative of the exponent. So we get there. When we integrate 2x dx, we're going to keep that constant out in front. I'm taking the integral of x dx. So I'm going to increase the exponent by 1, divide by that exponent, and so this is going to simplify to be x squared. So this setup seems more successful, so I'm now going to go ahead and bring out my formula and substitute into it. Now, when I get to this step and I look at the new integral that this process has created, I get a little sad because it looks like a mess. Certainly, we can multiply the x squared times the 2x and try and clean it up a little bit. So as I did my cleanup, I pulled my constant out, but still, what I'm staring at here is not better. I still have a product going on, so this is making me unhappy. So what then? Well, you may not like the answer, but you will learn a variety of integration techniques, and you can't be lulled into thinking, well, this section is on integration by parts, so I do every problem by integration by parts. Because realistically, when you're confronted with an integral, you're not going to know what technique is the right one to try. So it turns out that this integral is more simply evaluated using just regular u substitution. Here's why. When we choose our u, remember, when you have an exponential expression, you want to use the exponent as your u, and then you take your du. And right there is where I know this is what I want to do, because when I match up my functions, my u is here. And also, without even moving my constant to the other side, I have 2x dx matches 2x and dx. So therefore, I can rewrite this integral as the integral of e to the u, and the 2x dx all gets replaced by du. So that's a very easy integral to cope with. And last step, I just substitute u back in. So please understand, you've got to have full command of all these techniques. And just because one doesn't work doesn't mean you give up. It means you try something else. Now, in the next video, I will finally give you a little bit of guidance in terms of how to choose a u and dv that are likely to work.